Hi, everybody. So we're going to get started here on chapter 19. This is chapter 19 about acids and bases. This is the last chapter that we're doing. Okay, so that's the really good news about all of this. This is the last chapter of information that you'll need to take notes on. You should have some paper and pencil so you can write this stuff down. Again, this is a big chapter. There's a lot to go through. Right, so you're going to need to kind of keep up on all of this and let me know if there are things that just don't make any sense to you as we're going through this. All right, so chapter 19, there are 5 sections here, and we'll talk about the first section here in this first part of the notes. So we're going to go through and talk about what acids and bases are, right? What's the definition of an acid? What's the definition of a base? What are their properties? And then we'll get into some other things like pH and acid and base strengths, and then eventually reactions with acids and bases. Okay. We're going to start by talking about the properties of acids and bases, because acids and bases are things that you probably are already familiar with, even if you don't understand the chemistry behind them. Okay. So acids and bases are things that we probably are working with on a regular basis, especially in food or in cleaning products. Okay, so let's talk about the properties of acids to begin with, right? So acids are things that if you were to taste them, if they were in a food, acids are always tart or sour tasting. Okay, and I think you can imagine what we're talking about here. We're talking about like the taste that you would get out of like lemons, right? That would be a sour taste because lemons contain citric acid. In fact, most of the citrus fruits would have that same taste to them, although some of them also have sugars in them that kind of mask the sourness of them, right? Lemons don't have a lot of sugar in them, therefore they're pretty sour all the way around. Acids are electrolytes. Now, this is something that we did talk about, if you remember back in chapter 15, right? We were talking about solutions and different mixtures, and we said that if you dissolve an ionic compound in water, it conducts electricity, and that's called an electrolyte. Well, an acid is an ionic substance that's dissolved in water, therefore it is an electrolyte also, right? So that means electricity could pass through an acid solution. Right now, for this moment, we're going to define an acid as being anything that has H positives when you put it in water, right? When you dissolve it in water, H positives will actually dissociate or separate off of it. The H positives is one of the ions. Okay, we're going to find out that doesn't always have to be that way. We'll talk about that in a little bit. But for now, that's a general property of most acids. Acids also turn litmus paper red. Right? Litmus paper is a really basic substance. Litmus is a basic substance that has been around for ages, right? It's probably for thousands of years we've known about this substance. And litmus, when you soak it into a piece of paper and then you put the paper into a solution, the litmus can give you a general indication of whether you have an acidic solution or a basic solution. If it's an acidic solution, the litmus paper will turn red. And then finally, we know that acids have pHs that are less than 7 or pOHs that are greater than 7. We're going to talk about what both of those actually mean. You've probably heard of pH for a lot of times now in science. You may have never heard of pOH before. It's a really similar concept, and we're going to talk about it obviously in here, okay? Now, bases are just about the opposites of acids, right? So what's the opposite of sour tasting? And I know a lot of you in your brains right now are going, oh yeah, it's like salty or it's sweet. Well, it's not. The opposite of sour is bitter. Now, Most people have trouble thinking in their head what bitter tastes like because most people don't like the taste of bitter. Therefore, they try to actively avoid it in most of the things that they try to eat. But if you like really dark chocolate, it's bitter. If you like black coffee without any sugar or milk in it, that's a bitter taste. Some people think that broccoli or Brussels sprouts have a bitter taste to them. Those are generally people that don't like broccoli or Brussels sprouts, and that bitter taste comes from a base. So those are bases. They have a bitter taste to them. Another thing you could think of, and of course you should never do this, but if you've ever accidentally tasted soap, right? Soap is made from a base, right? Soap is very bitter. This is why people threaten if you said curse words too much at your house or whatever, your mom might have said, I'm going to wash your mouth out with soap. All right, so that's a bitter taste. Nobody likes that. You shouldn't do that, of course. That bases feel slippery. And we just said that soap has base in it. If you were to make soap, soap's a really simple substance. Soap is made out of two things. It's made out of a strong base and a fat or an oil of some kind. You can make soap literally at your house. It's that simple, right? You need some like vegetable oil or some animal fat, and then you would need some kind of strong base, and then you mix those two together and you'd actually make soap. That's what soap's made out of. Now, as you can imagine, if you simply made it out of just those two things, it would get you clean, but it would smell like oil or animal fat, which doesn't smell nice. You're clean, but it doesn't smell nice. So professional soap companies are actually going to put in lots of other things into your soap to make it smell better and all that kind of stuff. But the basics behind it, right? The average soap is base and an oil or a fat. If you were to put a base in your fingers, on your skin has oils in it, right? So if you were to rub a base in your fingers, you would start to feel slippery because it's actually turning the oils in your skin into soap, right? So bases feel slippery. Bases are also electrolytes because bases are ionic substances dissolved in water, and ionic substances dissolved in water can conduct electricity. Bases, as again, for right now, for this moment, we're going to define as usually containing OH negatives. If you remember back to when we talked about naming things, naming ions in this class, OH negative was named hydroxide. So an OH negative is called a hydroxide. And so bases oftentimes have hydroxides in them. They turn litmus paper blue, right? So bases turn litmus paper blue instead of red. And finally, the pH of bases is greater than 7, or if you're talking about the pOH of a base, it's less than 7. All right? So those are the basic, I shouldn't keep saying that. Those are the general properties of acids and bases, right? So here are some examples of acids and bases. You can see in the acid picture here that lemon juice, vinegar, vitamin C is an acid actually. And then I don't know what the other thing is. That is probably like some kind of baking powder of some kind. And then the bases side has a lot of cleaners. You can see you've got baking soda, you've got Drano, oven cleaner, and those are all bases. There's not a lot of food examples of bases. Here's some of the other examples, right? Acids are citrus fruits. Most tea is acidic. Battery acid, vinegar. Milk is actually a little bit acidic, just a little bit. If it gets too acidic, it tastes really sour, and then you have sour milk, right? And then if the milk gets really sour and it turns chunky, then you have sour cream. Okay, that's what that comes from. Soda, right? All the pop that you can think of is acidic. That's one reason why it's not good for your teeth, besides all the sugar that's in them too. Most fruits are acidic. Bases, and you can see all the examples of bases, things that we've already talked about, right? Baking soda. Lye. Lye is a common name for sodium hydroxide. Sodium hydroxide in lye, that's what they use to make soap, right? Ammonia, soap itself, right? Antacids, those would be bases. Okay? So now let's get into the chemistry of acids and bases. You know what an acid is. We just talked about the properties of acids. We know what a base is. We just talked about the properties of bases. But what makes them that way, right? What chemically makes acids do those things, and what chemically makes bases do those things? So let's talk about the definitions of acids and bases, chemical definitions. The very first chemical definition was developed by a very famous chemist by the name of Arrhenius. Okay? Arrhenius came up with some very simple definitions of acids and bases. And his definition of an acid was any substance that when you put it in water dissociates or separates into H positives. All right? So he says that all acids are substances that dissociate H positives when they're in aqueous solution, when you dissolve them in water. And he said that's what makes hydrochloric acid, HCl, an acid, because when you put HCl in water, it separates, it dissociates into H positives and Cl negatives. And the H positives make it acidic. It does all those things. It would taste sour if you were to taste hydrochloric acid. You shouldn't. It would conduct electricity because it has ions there. It would turn litmus paper red. It would have a pH of less than 7. All those things that we learned about acids, that's what hydrochloric acid does. That's why it's an acid. And then Arrhenius went on to say that a base would be any substance that dissociates OH negatives in aqueous solution. So those are those hydroxide that we talked about before. So if you dissolve a base in water, he says that a base will always release OH negatives into the water. So for instance, sodium hydroxide, NaOH, is a base, he says, because when you put NaOH in water, it dissociates, it separates, because the water molecules will surround those Na positives and those OH negatives and carry them off separately from each other as they dissolve. So it separates and you get OH negatives, and the OH negatives are what's responsible for the base properties. That's what makes it feel slippery and taste bitter and turn litmus paper blue and have a pH greater than 7. All those kinds of things happens because of that OH. Now, there was one itty bitty problem with these. Okay, these definitions are way, way, way too narrow of a definition. As more and more chemists were doing some experiments with acids and bases, they started to find that Arrhenius's definitions didn't hold true all the time. For instance, they found acids that did not have H positives in them, but still acted acidic. Or they found substances that had no OH negatives in them, no hydroxide, but still acted basic. Well, that's a bit of a problem. So Arrhenius's definitions, while really simple, were too narrow and they needed to be broader. We needed to expand what the definition of an acid and a base was. So there were two chemists, actually they did not know each other at all, that happened to be working on this same problem at the same time in two different locations. There was Bronsted and there was Lowry. Bronsted and Lowry, in separate locations, were coming up with new definitions of acids and bases based on experiments they were doing. And so we give them both credit. We call these the Bronsted-Lowry acid and base definitions. They said an acid doesn't necessarily have to dissociate H positives in aqueous solution. Really, an acid is anything that donates an H positive. Now think about that for a minute. Think about what the word donate means. Donate means it has to be given to something else, right? Donate doesn't mean that you just let it go. For instance, if you're walking down the street one day and you drop a $20 bill out of your pocket onto the ground and you keep walking, you did not donate that that $20 bill. You did not donate that. You just dropped it and lost it. So Bronsted and Lowry said an acid has to donate the H positive. By the way, if you're wondering why the word proton is next to the word H positive, I want you to think about this for a second. If you take a hydrogen atom, this is where you're going to need a periodic table. So if you don't have a periodic table sitting in front of you, take a moment, get out a periodic table for me, please. If you have to pause this, you can do that. But get yourself a periodic table, and I want you to look up hydrogen. Now, when you look up hydrogen on the periodic table, and maybe you don't even need a periodic table, maybe you have hydrogen memorized in your head. Hydrogen is atomic number 1. That means that it has 1 proton in its nucleus. Okay. Now, protons are positive, we know that. If you want to figure out how many neutrons a typical hydrogen atom has, you would look at its atomic mass, which is the other number at the bottom. So the other number, what we usually have been calling molar mass in the last few chapters, is 1.0079, right? So it's basically 1. So if you take 1 for the atomic mass and you subtract 1 for the atomic number, that gives you 0 neutrons. So the typical hydrogen atom doesn't have any neutrons. It has 1 proton, no neutrons. And then it would have to have 1 electron, right? So there would have to be 1 electron around the outside of this, which is negative, okay? So you have 1 negative electron around the outside, you have 1 positive proton in the center, and that is a hydrogen atom. Now, what if it's a hydrogen ion? What happens to that electron? That electron would have already gotten donated away. So if we don't have this, what's the only thing that's left in this hydrogen atom now? It's only the proton. So a hydrogen ion is also known as just a proton. So a lot of times we'll go back and forth in this chapter talking about H positives, or we'll talk about protons. They mean the same thing, okay? So an acid is anything that donates an H positive, otherwise known as a proton. And then if you were to look at hydrochloric acid, and you look at it from Bronsted and Lowry's perspectives, HCl is not acidic because it just lets H positives out into the water. It's acidic because the H in HCl gets donated to the water itself. You notice, you can see here in the equation, right, that the water goes from being H2O to H3O. Well, where'd the H come from? Well, this H here was donated by the HCl. Okay, so that's what makes it acidic according to Bronsted and Lowry. HCl doesn't just drop H positives into the water necessarily, it donates it to something else, in this case the water. So we can actually go through and label everything in this equation now. So the HCl is the acid, it does the donating. That means the H2O is accepting the H positive. That is known as the base, right? So the base is an H positive acceptor. So it's a proton acceptor. Anytime it accepts a proton, it's acting as a base. So notice that according to Bronsted and Lowry, bases do not have to have OH negative in them. On the contrary, they don't even have to have anywhere close to an OH negative. All they have to do is they have the ability to accept an H positive. That's always what the base is. Since an acid has to donate and a base always has to accept, then there always has to be an acid with a base, according to Bronsted and Lowry. If there's an acid around, then something else must be acting like a base to accept. And then notice what the other side looks like. The other side is also now an acid and a base. But we can't call those acids and bases also because we get confused. If there's 2 acids, 2 bases, nobody knows what they're talking about. So on the other side of the equation, we're going to put the word conjugate in front of it because the conjugate means related to. You notice that the HCl here in this example, the HCl donated its H positive to the H2O. The H2O turned into H3O. So the H2O acted like a base to begin with. and now has turned itself into an acid that's related to the original base. The HCl is now missing an H, so now it turned into a Cl negative. It went from being an acid to now being a base that's related to the original acid. Okay, so that's where the conjugate comes from. It's related to the original acids and bases that were on the other side. Here's another example of this, right? So in this example, let's see if we can go through and figure out which one's the acid, which one's the base, which one's the conjugate acid, which one's the conjugate base. So this starts off as NH3. We also know that as ammonia. Okay, we've learned that way back in the day, so hopefully that's somewhere in your brain. So NH3 is called ammonia. And if you put ammonia in water, it turns out that some of the ammonia molecules will accept an H positive. Now, how do I know they're accepting H positives? Because if I go over here and I look at its formula, it's no longer NH3, now it's NH4 positive. So what did it gain? It must have accepted an H positive. From what? Well, the only other thing around is water. So the water must be donating an H positive. So the water must be the base. Ooh, sorry, that's the acid. That's why we have things that are erasable. Let's try that again. So this is the acid because it's donating the H positive. The NH3 is the base because it's accepting the H positive. So just like we had up this upper example up here, the NH4 positive then would be known as the conjugate acid, right? Because it's related to the original base, right? Bases turn into acids, and then acids turn into bases. So this must be the conjugate base. We'll do that again in just a minute if you're a little confused on that. We'll look at another example of that again, okay? One vocab word that you should be aware of. You notice that water up here in my first example acted like a base. It was able to accept an H positive. And then in the second example, it was the one donating an H positive. It was acting like an acid. Since water can act like an acid or a base, depending on what it's with, it's called amphoteric. Right? So water is amphoteric. There are other amphoteric things out there. So you notice what happens even if you just put water with other water. If I put water with water, what does that mean? That means if I just have a glass or a beaker or a jug or whatever, or an ocean full of water, one water molecule and another water molecule will eventually donate, right? You'll have an H positive that's donated from one side to another, from one water molecule to another. And you'll get some water molecules that turn into H3O positives and some that turn into OH negatives. Right? This whole process is called auto-ionization, right? Because the water is automatically ionizing itself, turning into ions. Now, not all the water molecules do this, right? When you go drink water, you're not drinking a whole bunch of H3O positives and OH negatives, right? But a few of them do this. It's just a natural thing that happens. In fact, we're going to look more into this later on in this chapter because it's going to be important for us. Some other names, I want you to make sure that you understand what they mean, right? An H3O positive is a hydronium ion, is one of those ions that you should have memorized way back in the day. OH negative, we said already, is a hydroxide ion. H positive is a hydrogen ion, also known as a proton. Okay, so those are the names of ions that you should be very familiar with in this chapter. All right, you notice that this is the same equation that we were just looking at from before. But let's go through and one more time talking about how do we know whether something's an acid or a base or a conjugate acid or a conjugate base. And remember what we're looking for. We're just going to follow the H. It's kind of like one of those sing-along videos, right? You ever see one of those sing-along videos where the words are at the bottom? And so, like a little Disney cartoon or something like that, and they put the words of the song at the bottom, and then a little like rubber ball bounces from one word to the next word, telling you when to sing it in the song. This is what we're doing here. We're following the little H as he bounces along through this equation. So at first, this is NH3. This is H2O. But then on the other side, we notice that we have NH4 positive. So what happened to the NH3? It must have accepted an H, right? To go from this to this, it must have accepted an H. To go from H2O to OH negative, it must have donated an H. Once you figure out where the H went, you can figure out who's the acid, who's the base. Anytime something accepts an H positive, it must be a base. Anything that donates an H positive must be an acid. So let me do this in a little bit nicer way. So NH3, also known as ammonia, is accepting the H positive, also known as a proton. So it's acting as a Bronsted-Lowry base. The H2O, which we know as water, is donating a proton, an H positive. So it's acting like a Bronsted-Lowry acid. So we know that the ammonia is the base. We know that the water is the acid. Now, on the other side, these are always related. So NH4 positive is related to the NH3. If the NH3 was the base, then the NH4 positive has to be the conjugate acid, right? It turns out that now it has an extra H that it could donate back to the OH negative. The OH negative now is something that could accept the H back, which means it's now acting like a base, so we call it the conjugate base. And notice that there are always two pairs, right? There's a base that turns into a conjugate acid, and there's an acid that turns into a conjugate base. So we call these conjugate acid-base pairs. Always, every single time we talk about acids and bases, we're always going to have an acid and a base on one side and a conjugate acid and a conjugate base on the other side. And it's going to be your job to make sure you can identify which one's the acid, which one's the base, which one's the conjugate acid, which one's the conjugate base. Okay? So we're going to do just a little bit of practice with this so you get a little bit better at it. So let's start with this one. Okay, we'll do this one together, and then I'll give you a chance to do it on your own and see how well you do. So we want to figure out which one's the acid, which one's the base, which one's conjugate acid, which one's conjugate base. So we're going to follow along and figure out where the little h went. So we started off with NH3. It turned into NH4 positive. So NH3 must have gained an H. It must have accepted an H. If it accepts an H, it's the base. So I'm just going to put B here for now. That'll be good enough. HNO2, by default, must be the acid, right? How do we know? Because a base must accept from the acid. So the other thing that it's paired with is always the other. It's the acid in this case. Now remember, the base always turns into the conjugate acid. So the NH4 positive must be my conjugate acid. And the acid always turns into the conjugate base. You notice that once we figured out what the first thing was, once we figured out that NH3 was acting like a base, then all the rest of these kind of line up automatically. There's really no thinking you have to do after that. So these actually turn out to be really simple once you get the hang of figuring out one of them. Okay, so here's what I'm going to do. I'm going to put up another one here. And I want you to pause, and on your paper, I want you to figure out which one's the acid, which one's the base, which one's the conjugate acid, which one's the conjugate base. And then I'll put the answers up here in a minute. So go ahead and pause this, and we'll come back. Okay, so you've taken a couple of moments, and you've done this. You're looking at this, and you're like, oh yeah, CH3COOH on the other side turns into CH3COO negative. Well, it's missing an H. So it must have donated an H. So that means that the CH3COOH is a donor, and that's an acid. Well, if that's the acid, then OH negative by default must be the base. No more thinking involved. You know that has to be the base. And if CH3COOH is the acid, then whatever it's related to on the other side must be the conjugate base. And then whatever OH negative turns into on the other side must be the conjugate acid. Okay? Hopefully this is starting to sink in. Try this one. All right? You've taken a moment, you've tried this one. Here's the answers. The H2O turns into H3O, so it must have accepted. So that's the base in this case, which means this must be the acid, which means this must be the conjugate acid, and this must be the conjugate base. Let's see if I can fit it in there. There we go. All right. One more. Try that one. All right, so H2O, in this case, H2O turns into OH negative. That means it lost an H positive along the way, so it must have donated it, so it's acting like an acid in this case, which means the HS negative must be the base. So that means that OH negative must be the conjugate base, and the H2S must be the conjugate acid. Right? This is important because we don't want to spend a lot of time trying to figure out acids and bases, and they're not going to just tell you. They're going to give you an equation, and then they're going to start talking about acids and bases, and you need to be able to pick out which one's the acid and the base and the conjugate acid and the conjugate base pretty quickly. And you notice that it is a pretty simple process, but you do have to practice it a few times. Right? Oh, there was one more. Here, we'll just do this one together, right? CO3 negative 2 turns into HCO3 negative, so it must have gained an H, so that's my base. So this must be my acid, so this must be my conjugate acid, right? And this must be the conjugate base. By the way, you notice that I had an example where H2O was a base and then H2O was an acid. Remember what we called that? H2O is amphoteric. Do you spot something else in these examples? Sorry about the C there. Do you spot something else in these examples, another substance in these examples that acted like an acid in one case and a base in another? Hopefully you saw it. It's the HS negative, right? That hydrogen sulfide there is also amphoteric, because it can act as an acid or a base. All right, a few other quick practice ones. Let's say that I just gave you one substance and I asked, what's the conjugate acid of this substance? Well, if I'm asking about the conjugate acid of something, then I'm asking you to consider it as a base, right? Because bases always turn into conjugate acids. So essentially what I want you to do with this is I want you to think about if this were to turn into a conjugate acid, what conjugate acid would it turn into? In other words, if I want you to turn this into a conjugate acid, I want you to think of this as a base. What do bases do? What is their job? Bases always accept H positives. So if you were to put an H positive onto H2O, this would turn into H3O positive, right? So let's try another one. OH negative. What's the conjugate acid of OH negative? So again, if I want you to figure out the conjugate acid, then I want you to think of the substance as a base. And if it's a base, what do bases do? They accept H positives. So if I put an H positive onto OH negative, what do you get? You get H2O, right? Because the positive and the negative would cancel each other out and you just get H2O. All right, you try this one. This is a tough one. So if you were to do this one, you are accepting an H positive. Now, here's what a lot of people want to do. They want to make this a CH4. Right? And you can't do that. Why? Because this is inside these parentheses, and outside the parentheses there's a 3. So if I make this a 4, I didn't just add one H, I just added 3 H's. I only added one H. That's all I want to add is one H. So if I want to go through and add in an extra H into this example, this would have to stay CH3,3. And since there's nitrogen in it, I'm going to put the H at the end. Anytime there's nitrogen in something, generally the H's go at the end. So that would be my answer here. If I put an H positive onto that formula, that's what I would get. All right, one more. Try that one. What's the conjugate acid of S negative 2? Did you figure it out? So if I accepted an H positive onto S negative 2, the positive would bring the negative 2 down to -1. And so you'd have HS, and instead of -2, it would just be -1. Now, you should be able to go the other way too. So I want to know, what is the conjugate base of the following? So if I'm asking for a conjugate base, then you're taking these substances and thinking of them as acids. What do acids do? What is their job? They donate H positives. So if I take H2O and I donate an H positive off of it, what does it turn into? It turns into OH negative, right? If I take H3O positive, or if I take CH3COOH, or if I take H2S, and I want to know what's the conjugate base, you do those. You try those. Pause this for a minute and do those. Okay, quickly, here are the answers. So H2O, we said, turns into OH negative, right? H3O would now turn into H2O. CH3COOH, well, which H do we take? Well, we take the H that's by itself, so the H is at the end. If I take an H positive off, I'm left with a negative. Same thing here. If I take an H off of this, I'm left with a negative. Okay, very last thing. There is another definition of acids and bases that was come up with much later after Bronsted and Lowry. Because again, people started to find Bronsted and Lowry's definitions didn't always work. There were substances out there that did not have H in them at all and were still acting like acids and bases. And so Lewis, same guy that came up with Lewis structures, he he also came up with a definition for acids and bases that actually works in all cases. He says that an acid has nothing to do with H's or H positives or protons or anything like that. An acid really is just something that accepts a pair of electrons, and a base has nothing to do with accepting an H positive or having OH negative in it or anything like that. He says that a base is simply just a donator of a pair of electrons. Okay. So H positive is an acid, not because it's donating itself, like Bronsted and Lowry would say, but because it's accepting a pair of electrons. The OH negative there is not a base, even though that are not a base according to the other definitions, right? Because Arrhenius would have said that OH negative is a base because it's OH negative. Bronsted and Lowry would have said OH negative is a base because it's accepting an H positive in this case. But no, Lewis says a base is just something that donates a pair of electrons. So that would be the acid, that would be the base. But then if you gave Arrhenius or Bronsted or Lowry this example and you said which one's the acid, which one's the base, they would get totally confused, right? Because Arrhenius says, well, there's no H's or OH's here, so I cannot pick out which one's the acid or the base. Bronsted and Lowry said there was no H's to donate or accept, therefore there's no acid or the base. But Lewis says, yes, there's still an acid and a base in this example. Now, we're not going to use Lewis acid and base definition very often at all, okay? Because to do this, you would actually have to draw Lewis structures for everything so that you could see where the pairs of electrons are. Nobody wants to do that. Outside of Lewis, nobody wants to do that. So we rarely ever use Lewis's definitions because we just don't see them. It doesn't come up very often. Bronsted and Lowry covers like 95% of all the acids and bases we're ever going to talk about. It's good enough. So that's the definition I want you to know the best, okay? All right, again, start working on the homework problems for this chapter. Again, last chapter, so let that kind of spur you on so that you can get done with this stuff, all right?